Hello everyone. So today the RMO exam was there. So I hope you all did good. And so let's discuss the first problem of this paper, which is a number theory problem, and which states that you have this set S, where it has elements from n4. That means like a comma b comma c comma d, such that a square plus b square plus c square is equals to d square. Okay, so all are natural. So now you have to figure out like which the largest integer m which divides the product, okay, a b c d, for all such elements a comma b comma c comma d belonging to the set S. Okay, so the main idea to solve these type of problems is to figure out the minimal solution. Okay, so what do I mean by in terms of minimal? So maybe the sum of abcd might be very small, or maybe since here division is like we are I mean division is involved, so we might try to get some solutions involving like one or two primes, or maybe like two to three primes where they are involved, and argue that all such solutions should be divisible by those primes. So naturally the main primes that comes into these questions are like the basic ones, 2, then 3, even this is I mean those who have learned Pythagorean triple. So there also you see that we can argue that one like a square plus b square is equals to c square, so one of them will be even. So I mean you can have a structure of that, and that's the main idea behind these type of things. That is like I mean you can generalize, once you get a solution, then all those multiples are also solutions. So talking about a very talking about a very simple solution, which is like 1 square plus 2 square plus 2 square, which is 9, is equals to 3 square. Okay, so 1 comma 2 comma 2 comma 3 belongs to S. Now I can easily argue that like all other solutions will be having like here a is 1, I'm claiming, like a b or c, whatever. So out of abc, one of them is 1. It can't get lower than that because I'm taking from the naturals. Then the next one is like 2. Now you if you want to reduce it, so make it 1, and see it doesn't work. 1 square 1, 1 square 1, so 1 plus 1 2 plus 4. Okay, so it's 6. It's not a perfect square. And then even if you want to reduce this to 1, again you see it doesn't work. Okay, so any combination of any other combination of 1 or 2's doesn't work. So there you can very well understand that like you have to use either 2 or some higher numbers, if one of them is 1, so the sum gets bigger. So anyway, so yes, what so then the idea here is that like you see that this solution is involving primes like 2 and 3. Okay, so now this product is coming out to be what, 3 times 4, which is 12. Okay, so now this product ABCD itself is divisible by 12. So I can very well say that m is lesser than or equals to 12. Whatever if m is lesser than or equals to 12, because m should divide all the all such ABCDs. Okay, so I mean the product ABCD, all such products. So now let's argue that if I can argue that all the solutions will be divisible by 12, like the product ABCD will be divisible by 12, then I'm done. Okay, so now let's talk about 4 first. So I need to have 2 even numbers. Okay, then I'll be done. So talking about even numbers, so let's see, let's go with the help of modulo 4. So I have a square plus b square plus c square is equals to d square. Now when I divide any perfect square by 4, either the remainder is 0 or the remainder is 1. So when it's an odd number, the remainder is 1, and when it's an even number, the remainder is 0. As simple as that. Now try to look at the combinations possible. So on the left hand side, like the right hand side could be either 0 or 1 modulo 4. So the left hand side combination also has to be like the sum has to be 0 or 1 modulo 4. But now you see that like if the left hand side has to be 0, then all the 3 has to be 0, which shows that like all of them are divisible by 4, but I just need 2 of them to be even. So anyways, now let's come to the main point, that is like can all the three be odd? So if all the three are odd, like a, b, c, then you have a square plus b square plus c square would be congruent to 1 plus 1 plus 1, which is 3 modulo 4, and that can't be a perfect square. So then the next question comes, that can I have two of them to be odd? So in that case you will have like 1 plus 1 plus 0, like I showed that all three can't be odd. So can 2 be odd? So again this will be converted to 2 modulo 4. So again no perfect square when divided by 4 would give a remainder of 2. So again this case is not possible. So the 3 cannot be odd, 2 cannot be odd. So that means like at most 1 can be odd. Okay, so the thing is like one of them is odd, so 1 plus the other 2 will be even. So even square will be congruent to 0, and that will give us that d is also odd. Okay, so modulo 4. So we proved that 2 of them will be even. Okay, so the product is divisible by 4. I'm done with 4. Now coming to 3. Again under modulo 3, so again if I divide any perfect square by 3, so the remainders are either 0 or 1. Okay, so now again let's look at the combinations, as simple as that. So if I argue that okay, none of them, like a, b, c, if one of them is divisible by 3, I'm done. So let's argue on the contrary that none of them is divisible by 3. So that means what? All of them will be giving like all of these numbers a, b, c are either of the form 3k plus 1 or 3k minus 1, which is giving whereas their squares are giving a remainder of 1 modulo 3. So if that's the case, like 1 plus 1 plus 1, then it's congruent to 0 modulo 3. So which shows that d has to be then divisible by 3. Okay, so if ABC, all the three are not divisible by 3, then d is divisible by 3. And the other cases are like if one of ABC is divisible by 3, then I'm done already. So that implies that m is greater than equals to 3 times 4. Okay, and that proves that m is equals to 12. Okay, yeah, so that's the solution for the first one. So I'm solving the rest. So I just got the question paper. So yeah, as soon as I solve the rest, I'll be posting it. So yeah, so stay tuned, and yeah, thanks for watching, and keep watching and keep learning, and see you in the next one.